Hello everybody, today I'm going to go over this problem here which involves Kirchhoff's current law and Kirchhoff's voltage law. So first, going over what each of those is, Kirchhoff's current law essentially states that the total current entering a junction is equal to a total current leaving. So an example of this, if you have a battery somewhere over here, comes into a resistor, and then there's a junction here, and there's a resistor up here, and a resistor down here, and they rejoin. The total current right here is going to equal the total current right here. And then Kirchhoff's voltage law says that the sum of the voltage gains equals the sum of voltage drops around a loop. So let's say we have our battery, here's a resistor, very simple circuit. The voltage gained around the loop is going to equal the voltage drop from this battery. And the voltage drop from the battery is always negative. So to start out, we have a 12-volt battery connected to R1 and R2 in series. Between R1 and R2, a branch splits off to R3, which then reconnects after R2. The first thing it asks is to draw this exact circuit, and I would suggest doing that for any circuit that you deal with. So we have a 12-volt battery here, 12, say that this is the positive side, this is the negative side, goes over here, and then it connects to R1. So here is R1. And R2 in series, so that's one after another. So here is R2. And then it says between R1 and R2, so between the two, a branch splits off to R3. So we're going to say here is our R3, which then reconnects after R2. So they reconnect here, and then the circuit, of course, completes. So I'm now going to use Kirchhoff's current law at the junction between R1 and the parallel branch to find the branch currents. So there's three equations that we're going to need, and I'm actually going to derive them both from Kirchhoff's current law and from Kirchhoff's voltage law. So the first one we're going to need is the current here is going to equal the current over here. What that means is, let's say that over here current is I1, and then this is I2, and this is I3. So that's just like the current that runs through resistor 1, the current that runs through resistor 2, and the current that runs through resistor 3. It just means that I1 is going to equal I2 plus I3. And then this is our first equation. Now, Kirchhoff's voltage law says that the sum of voltage gains equals the sum of voltage drops around a loop. We actually have two loops going on here. I'm going to highlight each of them. We have one that starts here and then follows resistor 2 around. And then we have one that starts here and follows resistor 3 around. And then these are our two loops. So we have an equation for each of these loops. We have negative 12, which is this here, our voltage drop, equals the current, or sorry, not equals, plus the resistor 1 times the current that runs through resistor 1 plus resistor 2 times the current that runs through resistor 2 equals 0. And then that's from the red loop. And then from the blue loop, we have the same thing. We have negative 12 plus resistor 1 times the current that runs through resistor 1. You'll notice that both the blue and the red loop run through resistor 1. And then plus resistor 3 times the current that runs through resistor 3 equals 0. And then both of these can be rearranged by adding 12 so that it's on the other side. So we have R1 I1 plus R2 I2 equals 12. And then R1 I1 plus R3 I3 equals. So now we have our three equations here, which is perfect because we have three unknowns. We have I1, I2, and I3. All three of these are unknown values. So we can solve them for each other. So I'm first going to take equation 2 and I'm going to plug in the values for R1 and R2. R1 is here, it is 4 ohms. R2 is 8 ohms. So we have 4 I1 plus 8 I2 equals 12. And then I'm going to do the same thing for equation 3. R3 is here, it's 4 ohms. So we have 4 I1 plus 4 I3 equals 12. You may be tempted to just say, well, obviously for this equation here, 4 plus 8 is 12, so I1 and I2 have to be 1. But that's not actually the case, and you'll see why as we go through it, even though that would be very convenient. So the next thing we're going to do is I'm going to solve both of these equations in terms of, well, actually I'm first going to simplify both of them. You'll notice that everything is divisible by 4. So this first equation simplifies to I1 plus 2I2 equals 3. And this is just done by dividing the whole equation by 4. And then the same thing for the bottom equation, dividing the whole equation by 4, we get I1 plus I3 equals 3. So now that we have this, we can easily plug it into equation 1. Let's see, I'm going to choose to solve for both equations in terms of I1. So our top equation, 2I2, we'll subtract I1 and then divide everything by 2. So 3 minus I1 over 2 equals I2. And then the bottom equation is just 3 minus I1 equals I3. So now we have two equations here that are only in terms of I1. So we can plug both of those values into our top equation so that we have one equation only in terms of I1. So we have I1, I'm going to call this 4 so you can see where I plug it in, and this one 5. So I1 equals I2, so we'll use equation number 4 here because that equals I2. Plug it in, 3 minus I1 over 2 plus I3. I3 is right here. We have it as equation number 5. So plus 3 minus I1. So now it's just algebra solving for I1. So I'm first going to, you notice that we have two terms that are both 3 minus I1. So I'm going to factor them out. So I get I1 equals 3 minus I1 times 1/2 plus 1. And then these add together to just be 3/2. So we have I1 equals 3 minus I1 times 3/2. Distribute the 3/2. I1 equals 9/2 minus 3I1 over 2. I'm solving for I1 here, so I'm going to add 3I1 halves to both sides to get rid of it on the right side and move I1 over to the right side. And that's going to look like 5I1 over 2 equals 9/2. Now I can simplify for I1 by multiplying the left side by 2 and the right side by 2. Conveniently, they both cancel out. So then I just have to divide the left side by 5 and the right side by 5. And I end up with I1 equals 9/5. So I have I1 equals 9/5 now, and this is the hardest part of the whole equation because now I can easily solve for I2 and I3 using equations 4 and 5 here. So I2, 3 minus I1 over 2. So I2 is going to be 3 minus 9/5 over 2. Let's see, I'm just going to plug that into a calculator really quick because most of the time I like to put my currents in decimals anyways. So 3 minus 9 divided by 5, and then divided by 2. This is 0.6. And then I3 is just 3 minus 9/5, which is I1. This equals 1.2. And then 9 divided by 5 for our initial I1 equals 1.8. And all of these are in amps. So we have I1, I2, and I3. These are the currents that run through the respective resistors R1, R2, and R3, with I1 associated with R1, I3 associated with R3, I2 associated with R2. So now, question 3 asks us to apply Kirchhoff's voltage law around each loop to confirm voltage drop sums to 12 volts. So remember, we used Kirchhoff's voltage law to derive equations 2 and 3 here. So that's just asking us to plug it back in. So I'll check the first loop first, which is R1, I1 plus R2, I2 equals 12. R1 was 4 ohms. So we have 4 times I1, which is 1.8. And then R2 is 8 ohms. R2 is 8 ohms, and I2 is 0.6. I'm going to plug that into the calculator there. So 4 times 1.8 plus 8 times 0.6 does equal 12. So you remember I said earlier right here, be careful you don't just automatically sum numbers, because we found that I1 and I2 were not actually just equal to 1. They're equal to 1.8 and 0.6 respectively. So we're going to solve the last equation, equation 3, to verify that the blue loop satisfies Kirchhoff's voltage law. So we have R1, which is 4, times I1, which is 1.8, plus R3, which is 4, times I3, which is 1.2. Plugging that in the calculator, we have 4 times 1.8 plus 4 times 1.2. You'll find if you plug it in yourself, it does equal 12. So all of these currents that we found satisfy Kirchhoff's voltage law. And that's just a nice way to double check. Like if you're doing an exam, you can double check to make sure that you did your math correctly. And that's the end of this problem.